Hi, my name is Tom Heffel, and this channel is all about helping students learn chemistry. In this video, we're going to talk about calculating the pH of weak acids and weak bases. At the very beginning, we're going to do a strong acid so that we can do a compare and contrast of how it's different from a weak acid. So the first problem that I'm going to do is pretending that I have a jar or a beaker filled with 0.100 molar nitric acid. Now, nitric acid is on our list of strong acids. And a lot of this comes down to just good equation writing. So if I take my nitric acid, which is a strong acid, and I put it with water, and I write an equation for this, okay, it's going to be a single arrow, okay, because this nitric acid is going to donate all of its protons and everything's going to shift to the right-hand side. So the proton's going to be donated to the water to form hydronium, okay, and that's also going to create the nitrate ion. Now, because this is a single arrow, okay, I'm going to use something called a BCA, which stands for before, change, and after. And what I have here is the molarity of the nitric acid, okay? And what I know, it's going to shift all the way to the right, okay? Now, I got water in play here, okay? But it's not going to be a big part of the BCA, so I'm just going to leave it alone, okay? And this is going to shift all the way to the right. So all of this is going to go away, and there's going to be nothing left over. So there's actually no HNO3 in this container. It's just going to be hydronium ions and nitrate ions. So if this goes down by 0.1, this is going to go up by 0.1, and each of these are going to be 0.1. And the part that I'm most interested in is the concentration of the hydronium ions, because that's how we figure out our pH. The pH is the negative log of the concentration of hydronium ions. So I'm going to go ahead and plug in the 0.1 there, and I find out that this thing has a pH of 1, which sounds like a pH for a strong acid. Okay, remember at the very bottom of the pH scale, zeros and ones. Okay, that's the pH of a strong acid. Okay, so I want to make sure that we label this is how we deal with strong acids. And this was in our previous video, but I want to make sure in this video that we're comparing and contrasting what a strong acid versus a weak acid would look like. So I'm going to kind of do an apples to apples comparison. Here's my beaker, okay, and this time I'm going to have 0.11 molar of nitrous acid, okay, because the NO2, okay, that's the nitrite ion, so we call this nitrous acid, and this is a weak acid. It is not on my list of strong acids. HNO2 is not on that list from the previous videos, okay? So like I said, a lot of this is just good equation writing, okay? And so I'm going to take the nitrous acid, HNO2, and I'm going to put it with water, and because it's an acid, it still donates a proton, but it's not going to be a complete shift to the right. It's going to be a partial shift, and that's why we use an equilibrium arrow. Okay, but everything else is going to look pretty much the same, but I got the nitrite ion instead of the nitrate ion. Okay, now because of the equilibrium arrow, I don't use a BCA chart. Okay, I'm going to use an ICE chart, which stands for initial, change, and then at equilibrium, okay, where this is before, change, and after, okay, after the reaction, this is what's remaining. No HNO3, just the ions, okay? That doesn't happen with the weak acid, okay? For the weak acid, we're going to come in here and put our 0.100 molarity for the HNO2. We don't have to worry about the water piece, okay? But this is just going to shift a little bit to the right, okay? And I know that because I'm going to look up the Ka value in the textbook, and in the textbook, it tells me that the Ka value is 4.5 times 10 to the negative 4. And just so you know where I got that from, okay, most textbooks provide in the very back of the book an appendix that has a list of equilibrium constants. This page is for my acids. The next page is for the bases. Okay, so that's where I got that 4.5 times 10 to the negative 4. So this is a relatively small number, but I know it has to shift at least a little bit to the left, but I'm not sure by how much. So I'm going to put minus x, and then this is going to be plus x and plus x because of the 1 to 1 to 1 ratio. So this is going to become 0.100 minus x. This is going to become x, and this is going to become x. And I'm going to plug all that into my equilibrium expression. Okay. So the equilibrium expression, remember, is the products over the reactants. So that's going to be the H3O plus times the nitrite. Okay. Those are the products over the reactants, HNO2. And remember, pure liquids, okay, are not included in the equilibrium expression. Okay. Now, typically, I would do this. I would plug in X for the H3O, okay, plus, and then the X for the NO2, and then 0.100 minus X, and all of that is equal to 4.5 times 10 to the negative 4. Now, I can continue this problem, but I'm going to end up having you to use the quadratic equation, okay? And there's going to end up being a shortcut when dealing with weak acids and weak bases, and that's because this K value is really, really small. And since this K value is really, really small, we know that this shift to the right is going to be really small. So if this X value is like 0.00001 or something like that, well, that's not really affecting the molarity of the HNO2 because 0.1 minus 0.0001 is still going to be approximately 0.100, okay? Because this X is so ridiculously small, okay? So that's the assumption that we're going to use, and that changes this problem from something that requires the quadratic equation to something that does not require the quadratic equation. And this is a perfect, legit move in chemistry. If you're a little bit worried about, oh, I don't know if I should do that, at the end, I'm going to show you the difference of using the quadratic equation versus using this approximation method, okay? So what I'm going to do is I'm going to cross multiply. So x times x ends up being x squared, okay? And that's going to be equal to the 0.100 times the 4.5 times 10 to the negative 4, okay? Now I'm going to multiply these two numbers and then take the square root, okay? And when I take the square root, okay, I get x equal to 0.0067, okay? Now this 0.0067 is the value of the hydronium ions, okay? And remember, we can just take the negative log of this to figure out the pH. So pH is the negative log of the concentration of the hydronium ion. So I'll take that 0.0067 number and take the negative log of that, okay? And if I do that, I get a pH of 2.17, okay? So the pH of this problem ends up being 2.17, which is higher than the 1.0, and that's because this is a weak acid, okay? Now, the smaller this value gets, okay, the shift is going to be less to the right, okay, and that pH will start to rise, okay. But just wanted to show you kind of a compare and contrast between a strong acid and a weak acid and what we have to do, okay. Now, if we use the quadratic equation, because I said I would do a comparison of this, if we use the quadratic equation, okay, this value for x would come out to be 0.0065. So you can see it's only off by 0.0002, okay, which ends up being fairly insignificant, okay? So just want to make sure that you guys understand that the quadratic, not using the quadratic equation and doing the approximation method is perfectly legit, okay? Now let's switch gears and do a weak base. So I'll leave my weak acid up here, and I'm going to erase the strong acid so that we can do a weak base and see the differences between a weak acid and a weak base, okay? So the problem that we're going to do is we're going to have like a beaker filled with 0.15 molar NH3. And I have to recognize that NH3 is not a strong base. This is actually one of our weak molecular bases that we've memorized, okay? And it all starts out by writing a good equation for our base equation. Now, something that we know about bases is they accept protons. So you have to write this equation. It's required. You would have to write this equation with water because that's where it's going to get its proton from, okay? So this base is going to accept the proton, and when it accepts the proton, it makes the ammonium ion. Now, when this proton goes away to the ammonia, what's left over is going to be hydroxide, okay? And we're going to set up our ice chart, and the reason we're using an ice chart is because we have an equilibrium arrow. The initial molarity of the NH3 is 0.15. We're not going to worry about the water. And we kind of have the same setup here, okay? But one thing I want you to recognize is the product over here is going to be hydroxide with the base instead of having the product be protons or hydronium ions with the acid. So that's going to be the major difference between the weak acid and the weak base that I have over here, okay? Now to finish the problem, we know that there's going to be a subtle shift to the left or to the right. So this is going to go down. So this is going to be 0.15 minus x. This is going to go up x. This is going to go up x. So we got x. And we got to figure out, can we approximate here? So I have to look up the Kb value. And when I look up the Kb value, it ends up being 1.8 times 10 to the negative 5. Okay. Now, I want to remind you, I looked up this value from my appendix from my textbook. Okay. So that's not a number that came out of the thin air. That's something that I found in my textbook. Okay. And if the approximation method was okay when it was times 10 to the negative 4, okay, then I should feel really good about the approximation method if it's times 10 to the negative 5. So down here, I'm going to say, hey, this 0.15 minus x, it's approximately 0.15. And that's going to take this problem from being required to use the quadratic equation to not having to use the quadratic equation at all. Okay, so to finish up this problem, Kb is equal to the products over the reactants, which is NH4 plus and OH minus, all over the reactants, which is NH3. Remember, we're not including water because water is a pure liquid, and we do not include pure liquids in our equilibrium expression. And then we just sub everything in. So x here, and 0.15 here. So x and 0.15, and that's all equal to my equilibrium constant of Kb, which is 1.8 times 10 to the negative 5, okay? I'm going to cross multiply, and I get x squared is going to be equal to 0.15 times 1.8 times 10 to the negative 5. I'm going to multiply these two numbers and then take the square root, okay? And when I do that, I get x equal to 1.64 times 10 to the negative 3, okay? Now, I want to remind you, okay, that x is equal to hydroxide, okay? So this hydroxide value is going to be 1.64 times 10 to the negative 3, and this question is all about calculating the pH, okay? Now, there's two ways that I can figure out the pH from the concentration of the hydroxide ions, okay? The way number one is by using this equation that Kw is equal to the concentration of hydronium ions times hydroxide ions, okay? And I'm going to plug that number of 1.64 times 10 to the negative 3 here. I'm going to put hydronium here, okay? And then Kw is 1.0 times 10 to the negative 14, okay? And I can use this to solve for the hydronium ions by dividing by 1.64 times 10 to the negative 3 on both sides. And I find out that hydronium ends up being equal to 6.098 times 10 to the negative 12, okay? And if I take the negative log of that to calculate the pH, okay, so remember pH is going to be the negative log of this number. I get a pH, hopefully you can see that at the very, very bottom, of 11.21. Okay, so that's the way, number one, that I could figure out pH from this value, okay? Or I could figure out the POH, okay, because POH is the negative log of the concentration of hydroxide ions. And if I plug this number in right here, I'll find out that the POH is equal to 2.79. And then I subtract 14 from this to figure out the pH, because pH plus POH is equal to 14. So if I have the POH, 14 minus 2.78 gives me a pH of 11.21, okay? So didn't matter which way I did it, I'm going to get a pH of 11.21, which sounds like the pH for a weak base. That sounds appropriate. It's above 7. It's not at 14 or 13 like a strong base would be. So 11.21 sounds perfectly acceptable for a weak base, okay? So if I use the quadratic equation, okay, if I didn't do the approximation, like if I did 0.15 minus x right here, just to let you know, the x comes out to be 1.63 times 10 to the negative 3. So, I mean, those values are basically the same. It's not really, it probably won't even change the pH at all. So the approximation method, no problem, as long as we have something that's times 10 to the negative 5, times 10 to the negative 4, and that our molarities are somewhat reasonable. If you found this content helpful, please give it a like and subscribe. And when you add that comment, it really does push this information out to other students that are interested in learning chemistry.